So graphs, we're talking about graphs today, but not those graphs. So let's see, we're discussing graphs in computer science, but what kind of graphs are we talking today? So today we're talking about graph data structure inside computer science, which is a big cornerstone of a lot of theoretical computer science, algorithms, etc. We're not talking about bar graphs, pie charts, things like that, the visual representation of data. Many times as we'll say, oh, give me a graph, draw me a graph. That's not what we're discussing. Rather, we're discussing the graph data structure. So what is a graph data structure? Formally speaking, in mathematics, in computer science, it is a pair of vertices and edges. The representation is not usually that important, but rather we're given a finite set of vertices. It can be infinite graphs as well, but for the moment, let's look at the finite set of vertices, which is a set of vertices, the set E, which is a set of edges. Each edge connects two vertices, V1 and V2, which are in V. That's basically what a graph is. So graph can be directed or undirected. That means the set of the edges can be V1, V2 in an ordered pair, or V1, V2 in an unordered pair, a set. And this is an example graph. If we had to relay this graph to you, I could just say, hey, I have 1, 2, 3, 4, 5, 6 vertices. I have 5 edges. One edge connects V1 and V2. Another one connects V2 to V3. So even without giving you any kind of a visual representation, I could transmit to you the information, mathematically speaking, that this is a set of vertices, this is a set of edges in plain English, and that would be considered a graph. This is the graphs we are discussing. So there are some standard graph definitions. Let's talk about them first. When we say that xy is an edge, then we say x is adjacent to y, or y is adjacent from x, if it's a directed edge. If it's an undirected edge, we just say that the two vertices are adjacent to each other, and that's all we say. Or we can also say they're neighbors of each other. If the graph is directed, that means the edges are directed, then we use this concept of an in degree of a node x. How many edges are coming into x? Out degree, how many edges are going out of x? And if the graph is undirected, then we simply say degree, which means how many neighbors are there. Because the edges don't have direction, then we would just talk about the number of neighbors. A path is a sequence of nodes such that each vertex is adjacent to the next one, etc. And it can be directed or undirected. And the length of the path is defined by the number of edges. So if you have V1 to V2, V2 to V3, V3 to V4, that's a path of 3 edges, so the length of the path is 3. It can also be a cycle, which begins with a path that it's a path that begins and ends at the same node. The distance is the length of the shortest path from x to y. While you may have a longer path, the shortest path is what we would call the distance. Here's another example of a graph here. Here's a graph N with 4 vertices, 5 edges. And we can also now see, we're talking about a new concept called faces. And this one has 3 faces because it divides the entire landscape into 3 different areas here. The outside area, the upper triangle area, the lower triangle area. Those are 3 faces. This graph is planar because it can be laid out on a plane such that the edges don't cross over each other. Such graphs are called planar, and it's a fun exercise to prove that for a planar graph, n minus m plus f is always going to be equal to 2. So for example, if you add another vertex out here, and you would add another node, another edge, the faces would not change. Then you add another edge over here, the number of faces would increase by 1, but so would the number of edges, etc. So you can do all that kind of fun exercise to prove that n minus m plus f is equal to 2. There are 2 kinds of broad graph representations, even though there are others as well, but these 2 give you a little clue to what is at stake here. So when you want to represent a graph, you can represent it by an adjacency matrix. So essentially it's a matrix where you have as many vertices and rows and columns, and just put 0, 1 here if that vertex is connected to the other vertex. So you create a big array big square array, as many vertices on the left, on the rows, as many as you have the columns. So you connect those two vertices. If the two vertices are connected, you put a 1 there. If they're not connected, you put a 0 there. So this is called an adjacency matrix representation. You can also have an adjacency list representation, in which you simply create as many records as you have the number of vertices, and then just put a linked list which vertices are connected to it. So that's an adjacency list representation. Which one is better than the other just depends upon your use case. The adjacency matrix is very efficient to try to access, but of course it's a larger data structure. You may not have that much memory, especially if you have many vertices. And most graphs that you will come across will be sparse. That means the number of edges will be very few. Then adjacency list may be a better, more efficient choice. And like I said, there are many other representations as well. These two are a little bit of two extreme representations. Let's continue going further. There is binary, there's just a tree. A tree is a connected acyclic graph. That means it has no cycles, but it's still connected. Incidentally, if a tree is not connected, that means you have different components. We call that a forest of trees, where each component would be called a tree here. But here what we're looking at is a tree. Here's a rooted tree in which one node is designated as a root, the top node, and then all the other nodes kind of, come down from it. This is a little bit of a visual representation of a tree. So you can have a tree, and if you designate one node as a root, then it becomes a rooted tree, and then you kind of helps you draw it out like this. So here node A is the root node, there is two child nodes, these child nodes, etc., etc. Now this tree, you can see this node has 3 child nodes, this one has only 1, and that's perfectly fine. Many times people have studied binary trees, etc. I'll cover that in a moment again. But in general, when we talk about a tree data structure is just an acyclic connected graph. A tree has its own set of definitions. A leaf is a node that has no child nodes. Ancestors for a rooted tree are the nodes, all the nodes, including the node itself, going all the way up to the root as you go traverse up to the root. The subtree is the entire tree that can be considered rooted at that particular node. The subtree rooted at X is the tree consisted of X and all its child nodes and all the grandchild nodes and all that. The height of the tree is the maximum distance from the root to any node here. And now coming to binary trees, because these are something that people are many times very familiar with. A binary tree is a tree where each node has at most 2 child nodes, and there's a corresponding concept of binary search trees when we start storing values in these trees, etc., in each node, and then if we order them, then become binary search trees, and there's a whole another lecture on that, and you can kind of refer to it. But from an overall data structure perspective, this should give you a very brief overview of what are graphs, what are trees, and how to use them. And these data structures play a very central role in the study of algorithms, and they come up often. So it's useful to kind of review this material every once in a while. Thanks, have fun, and keep learning.